Okay, so this is a very lightweight talk for the very last talk. This is understanding your processor, a very lightweight topic to talk about. So I'm representing ACCU York, and a very quick disclaimer. Which way do you click it? Right, so this talk is my own views and opinions. Please do not take it as a reflection upon my employer. Everything in this presentation is as I give it to you. Please forgive me for any mistakes or omissions that I may make. So I work for IBM, and IBM do lots of cool stuff. In the background image there, you can see a quantum computer and a mainframe. I'm not that exciting. I don't work on that type of stuff. I work on a database. So a lot of you in this room are probably application developers. You probably use a database as your back-end persistence layer. And the story here is quite simple. You store your data in a database, and you later on retrieve that data. But not quite. Because if you're moving data backwards and forwards, this is quite expensive. So what you really want to be doing is leaving the data where it is in the database and doing computation and operations on that data and just getting back the small amount of data that you actually care about. So what I actually care about is computation. I want to make those operations and calculations going on in the database as fast as possible so you, as application developers, can leverage that for whatever your application is doing. So this is why I care about performance, but you lot as an audience have a wide range of expertise and backgrounds, and so I want to talk about performance, and I can't get into every single little obscure thing about every single programming language. So I'm going to take a step back and talk about something completely obscure, where the computation actually happens. Doesn't matter if you are Windows, Mac, or Linux. Doesn't matter if you're a memory managed language or not. The computation has to happen somewhere. And sure, some of you are using FPGAs or GPUs, but most of us are on a common processor, and real physical hardware does the compute for us. So in the same sense of when you get a really smart third-party library, and inside of there are wonderful algorithms and magic that's going on, you don't care most of the time. You're programming against an interface. That interface is what you're programming against, and every now and then, maybe you do want to look at the internals of the library so you understand it some better. But most of the time, you don't care. The same is happening with your processor. You're sending instructions, machine code and assembly, down to your processor, and most of the time, you don't care. But what I'm going to actually do now in this talk is actually give you an intuition about what's happening inside your processor, the little tricks going on to try and make all your programs faster. Not that I think you need this, but it's fun and interesting. So I'm going to do this by a few demos. The very first demo here is just adding in a random order. And I'm going to give you the explanation of the demo and some benchmark about it and build up your intuition based on it. So we have an array of data, and we're going to visit every single location in that array exactly once, read from it, and add it to an accumulator. But we're doing this in a random order. So all it's doing is read add, read add, read add, read add. You get the idea. So then I'm going to give you a benchmark that looks like this. On the bottom axis, what we've got is total bytes. So this is how small or large your data structure is. Is it a small array or is it a large array? On the other axis, we have bytes per second. So this is how fast are we doing the operation on our data structure. Right at the top, it's going like 20 gigabytes per second. At the bottom, it's going 450 megabytes per second. But, this is the rate that we're doing in operations, and all we're doing is reading from a memory location and adding it to an accumulator. This should be completely invariant of whatever data structure size we're working on. So what is going on here? Because quite clearly, it's not a straight line, it's not flat. The performance is dropping off. To build up your intuition, this is a logical representation of the architecture of my CPU. This benchmark does not care about multi-threaded. So even though there's 4 cores on my computer, I'm going to eliminate them to simplify the diagram. And again, inside a single core, it's hyper-threaded. Again, we're not doing multi-threaded code here, so let's eliminate that. We have a data cache and an instruction cache down at the L1. This benchmark is all about data. We don't care about the instruction cache, so let's simplify it and get rid of that. So what's happening with your processor is when it's trying to fetch memory, it is going to the nearest location of memory where it can go find it. So it's going to the L1 cache first and hopefully finding it there. If it doesn't, it goes even further away to the L2, L3, and then all the way eventually out to main memory. But it takes time to go fetch memory. So the L1 data cache is the fastest round trip time you can expect. And then L2 takes longer, then longer, and then longer. And then you're out to your main memory where you might as well be talking to a different planet. So this hopefully helps you understand what's happening in this graph. That dotted yellow line there is my L1 data cache at 32K. When our data structure is smaller than the 32K, it exists completely within the L1 cache. And therefore, we get that flat line that we expected. Because for every time we're trying to fetch data, it doesn't have to go very far to find it. It goes just to the L1 cache and then back to your processing core. Sometimes, though, your data structure doesn't fit completely in with the L1 cache, and therefore you need to go to higher cache levels to store it completely. So there we have the L2 cache line. And we know that when we're trying to find data in this data structure which is smaller than the L2 cache size, we don't have to go as far as the L3 or beyond. It's bounded to the L2 cache, but some of the times when you're trying to find your value, it will be there in the L1 cache. So this gives you an understanding of why the performance starts to drop off. And so the takeaway from this so there's the L3 and the L4 and then off to main memory. So the takeaway you should get from this is to try and make your data structures as small as possible. And you should be doing this for two reasons. One, for the exact example that I've got here, which is you've got a bit of data that you're using again and again and again. You want that small and hot within your L1 cache. But also if you've got a large data structure and you've just pushed it all the way through and you're just going to use it once, what you've ended up doing there, you've pushed every other bit of data out of the cache and you've basically been a bad citizen on the rest of your program. Because some other part of your program that needed that now has to go fetch that all the way from main memory and you've just slowed down the rest of your program. So the next little demo we've got here is a slight twist on that. Rather than going in a random order, we're now going to go in a sequential order. So even simpler. We go to the first element, then the next, then the next. Nice and simple. This has a significant enhancement on your performance. We are managing to sustain that really high bytes per second for much larger data structures. So this is something different that's going on in your processor. This is not the same as the cache effects that we had before. So our simple mental model of reading from memory is that when you want to read something, you go fetch exactly what you need. But hardware implementers know that the way that programs tend to work, if you're going to read a value in memory, you're probably going to read another value which is physically located somewhere near that value you've just read. So this is the idea of spatial locality. And so rather than just fetching what you asked for, it will fetch a whole cache line at a time. And so this makes sense for two reasons for your software programs. One, the exact thing in the benchmark where we have an array of data and you're going to go consecutively through that data, you might as well go fetch more than what you need right now. But it also makes sense in a lot of programming languages where you've got classes and structs, and the ordering in your class and struct of your data members in a lot of languages corresponds to the layout within physical memory. So you have data members that you're going to use together. So when you're actually doing this computation, the very next read that you need to do, there's no fetch required because it's already been fetched for you. This is not the only thing that's going on inside your processor. It is looking at your memory access pattern and it's realizing this is nice and predictable. So what we're going to do with that is the processor is going to make an assumption that you're going to continue accessing memory the way that you have been, and it's going to go prefetch that for you in the hope that you're actually going to continue executing through memory and reading memory the way that you have, and you're going to hit that memory. And so at the same point that you're in parallel doing your computation with the data that you already have, the prefetch is going away, fetching that memory for you, so that by the time you do need it, it is being fetched for you, and you don't need to wait when you get to there to say, go fetch it for me. And the prefetcher is still working on behalf of you to try and fetch the data that you require. Takeaway message from this is please take advantage of the spatial locality which is assumed by your hardware and try and make your memory access predictable. So, in that situation, if you're on one of those programming languages where the ordering of your data members corresponds to how they are laid out within memory, please do not sort them alphabetically. That is nonsense. What you want to be trying to do is group them by common usage so that they happen to exist within the same cache line. So the final demo that I'm going to give you here is conditional add. So this benchmark was done in a completely different language than the other two that I did before. But all we're doing in here is we're going across an array of data, and these values are going to be between 0 and 255. And so this condition that we have in the middle of this, half the time we're going to add that value, and the other half of the time we're going to do nothing. And so the only thing we're going to do in this benchmark is, before running it, we may sort the data or we may leave it unsorted. So the array is sorted or not. And this has a a big impact. So the sorted data is that blue line on top, and it's like 6.5 times faster than the unsorted. So, what's going on here? So the processor is basically playing a game, it's betting. And so it's basically looking at this code, and it is seeing that this is a nice tight loop which is going around again and again and again. And it's looking at this conditional thing and going, what if? We don't even know what it is yet. We've not done the computation to work out, is it less than or greater? We've not, done any of this, but what if? And so there's two assumptions it can make. The first assumption is it's going to be true on this iteration of the loop, and the one after, and the one after, and the one after that. Given that's the case, what we could do is actually just treat it like our sequential add. It's going to go away, and it's going to do all this addition into an accumulator, assuming that it's correct about its prediction. The other assumption we've got is false, and therefore we don't need to do any work at all. So this is two parts of your processor working together. We have the branch prediction, and this is the bit where it's playing a game. It's trying to work out what we've seen before, can we predict what's going to happen in the future? It's not clairvoyant, it can't get it perfect, but it's trying to get an understanding about what could happen. And based on the fact that if it got that bet right, if it's predicted completely correct, it's actually going to inform the speculative execution. Go ahead and do some work now with the hope that you're actually going to need it. Okay, so if you're correct, you've done the work before you knew you needed it and you've got to speed up because of it. But if you're wrong, then you've got to kind of do additional little work to clean up all that other calculation that you've done to give back the data that you was actually expecting. This is all done magically by the processor for you. You don't see any of this. So you can see with our random data, we get quite a lot of branch mispredictions. It's gone away and it's done all this additional work when it's gone, sorry, I'm wrong, I've got to roll back and fix things up. Whereas with our sorted data, sure, we get a couple of mispredictions, but most of the time it's correct. And when it's correct, it's actually doing that work that you did need before you knew you needed it, and you've gained a benefit because of it. So the takeaway message here is try to make your branches predictable. So this benchmark was unfair. It was a 50-50 chance the branch predictor isn't ever going to learn anything useful that it can exploit. So you want to have, predictable branches where it's going to be 90% true and 10% false, and then the branch predictor will learn and do the right thing. The other thing you should be doing is trying to reduce the number of branches in your code base. The only reason why we're trying to do this is because we're trying to fill up our instruction pipeline with useful work to do. And what we're doing is going, 50% of the time, this is going to be useful. And what you're doing by eliminating branches is going 100% of the time, this is useful, and there's never going to be that cleanup work needed. So now you kind of somewhat understand a little bit about caches, cache lines, prefetcher, spatial locality, the branch predictor, and speculative execution. And so what I hope you get out of all this is, this stuff is fun, hopefully. I also hope this was informative, and I really, really, really hope you do not need to know this stuff on a day-to-day basis. So, thank you.